Hello everyone, this is chapter 10.1 and it's a section on curves defined by parametric equations. To be quite honest, I think this is going to be a fairly straightforward section, maybe a little short of a video, but it's basically an intro on what we'll be seeing a lot in this section to do with graphing things a different way. And the first one we'll be seeing is this, which is parametric equations. And it's, again, fairly straightforward. Basically, if you have a curve, normally we have f of x, so we plug in an x value, we get a y value. In this case, we don't do that. Instead, x and y will be functions of a different variable, usually t, it could be something else, but usually it's t, and you plug t into each of them and see where your x and y coordinates are for a particular point, then you plot that point. That's essentially the idea. So here I give a visual where we have this curve, and we have a certain point that I'm emphasizing on, that's x comma t, but notice to emphasize on the fact that x and y each are a function of t, I write x of t and y of t. Okay. So one can think of t as time, and as t increases, basically as t moves on towards infinity, the point will move in a certain direction. It's not always the case that it'll move in the positive direction, it may move in this direction. So just to emphasize on that, let me draw some arrows just to show the direction. So let's just say it does move in this direction, but it doesn't necessarily have to. The other thing is that there may be restrictions on t, as we'll see soon enough in this example. Just because t kind of represents time in some sense, doesn't mean that t always has to be positive. You could plug in negative values of t, any real number will do really, and then you'll get a certain value for x and y individually, and you plot that point, like I said, so it follows a point. Anyways, let's move on to this example here. So I say graph the curve defined by the following. So I have a function for x, function for y, each in terms of the variable t, and it says only to plug in t between 0 and 4. Now, t being in between 0 and 4 doesn't necessarily mean that we only have to stick to integers. We can plug in 1/2 if we wanted to, for example, because it's a real number between 0 and 4. But what I'm actually going to do here is maybe the obvious thing to do. I'm just going to plug in t to be the integers in between 0 and 4. So namely 0, 1, 2, 3, and let's see if we make it on the board here, 4. Yeah, so perfect, it comes out. So now we're going to plug in t being these numbers into x and y. So for 0, x will be 0, y will be 1. When you plug in 1, you will get, let's see, 1 squared is 1, minus 3 is going to be negative 2 for x, and 1 plus 1 is 2 for y. When you plug in t equals 2, on the top you get 4 minus 6, which is negative 2, and 3 for y. Okay, plugging in 3 gives us, let's see, 9 minus 3 times 3 is also 9, 9 minus 10 is 0. Very good. Plugging in 3 here, 3 plus 1 is 4. And then finally plugging in 4. 4 squared is 16, 4 times 3 is going to be 12. 16 minus 12 is 4, and plugging 4 into y will give us 5. So now we're going to plot these points, and let's see what we get here. Okay, I just want to be careful on how I scale things, but I think that's a fair scaling. Probably should have made it a little lower. Let me make the x-axis a little lower, actually. Okay, that's fine. So notice the x values go between negative 2 and positive 4. Negative 2, negative 1, 1, 2, 3, and let's say that's 4. And the y values go from 1 to 2 to 3 to 4 to 5. All right, so let's take a look and see what this looks like. Let's just plug in starting with the first one. 0, comma 1 is up here. And then negative 2, comma 2. Okay. And then negative 2, comma 3. Right above it, then 0, comma 4, which is over here, and then finally 4, comma 5. Okay, good. Great. Now the only thing is it's a curve. It doesn't go straight up at this point. And I'll show that in a little bit, and I'll kind of emphasize on why that's the case and how I know that happens. But the curve will look somewhat like this sideways parabola. Like this. It doesn't look really pretty, but imagine it is if you want. It's fine. There we go. And yes, there is a direction. What is the direction? The direction is, well, just following the points in the order we got them, So in red, let me draw with arrows here. So we're going in this direction, from this initial point to this final point here. Sometimes these are called the initial and terminal points, where you start and where you end. But that detail isn't super important. The real emphasis I want to make here is that there's a direction, and then you plug in t values to get those points. Now I'm going to show another way we could have gone about this that's less obvious, but it has to do with the other big thing in this section besides just graphing. All right, so the next thing I want to talk about is what is called eliminating the parameter. By the way, t, the variable t, is known as the parameter variable. And to eliminate the parameter is to write, well, the equations x of t and y of t as one new equation only involving x and t. So combining x of t and y of t into an equation with only x and t, in other words, there's no y anymore. Doing this sometimes may look a little funny and actually may change things quite a bit. Usually what I give people the idea of is that when you eliminate the parameter, you lose information that the equation separately actually gave you. But if you're really careful about it, you don't lose any information, but you may get pluses or minuses. It could get a little messy sometimes. Okay, here's an idea I want to give you though. So this doesn't always work, but it works for the most part. So try to solve for t in one of the equations and substitute this into the other, because then t will be gone, and then you can try to simplify things to have a nice equation in terms of x and y only. So let's see if we can do that for this example. And notice, these are the equations we just saw in the previous example. And what I want to do is use this idea here. And solving for t in the first equation is difficult because it's quadratic. You could try to complete the square maybe, but let's not do that. Let's instead solve for t, so keep my idea in mind. Solve for t in this equation, so it's y minus 1. There we go, y minus 1, subtracting 1 to the other side. Then plugging this into the top equation, we will get x is equal to t squared is now y minus 1 squared minus 3 times y minus 1. So if we look at this equation now and we try to simplify things, what do we get? Well, we'll get x is equal to y minus 1 squared is y squared minus 2y plus 1. Good, that's just expanding it out. Distributing the negative 3, we get negative 3y and positive 3. Positive 3. And good, so now combining like terms, these combine to 5y and these combine to 4. So it's y squared minus 5y plus 4. And if you think about it, this looks like a quadratic equation. So imagine if x's and y's are swapped, it's a quadratic equation in x, which is a parabola, facing a parabola. But since x's and y's are swapped, it's actually facing in the positive y direction, which, if you take a look back at the curve we graphed, it's exactly that. In fact, if we wanted to keep this bit of information here, well, notice since t is y minus 1, this now becomes y minus 1 in between 4 and 0, possibly equal to them. If you add 1 to both sides of this inequality, you get the y is in between 1 and 5. And if you go back again in that example that we just saw, the y values are indeed in between 1 and 5. If you want to find the x values, well, just plug in 1 and 5 into this and you'll get the lower and upper x values. That actually doesn't really quite work because there may be some x value that's not accounted for when you do it that way. So that part of it's a little trickier. But at least we get some type of bound. And we'll do another example where things aren't as nice, and I don't think this idea will work as nicely. And we'll even take a look at how to graph that in both of those ways. One by plugging in and trying to follow the point, and the other by taking advantage of what we know in the usual type of equations involving x and y only. So let's take a look. All right, so for this example, we have the equations x is equal to sine of 1/2 theta, y is equal to cosine of 1/2 theta, and theta is in between negative pi and pi. The first thing you'll notice is, of course, we don't have t. And I said it's possible you have a different letter. Here the parameter variable is theta, which is fitting because they're trig functions, of course. And now the question is, how do we eliminate theta? Well, if you try to use my idea before and try to solve for theta in one of them, then you'll have inverse trig functions, and it's actually doable, but it's a little hard, and there's something a little better. And basically, when you have trig functions involved, you can always try to use trig identities to make things work out nicely for you. And in this case, what do sine and cosine have in common? Or at least, maybe not what they have in common, but what trig identity do we know and love that involves only sine and cosine? And you better be screaming out, you probably are screaming out, Pythagorean identity. The Pythagorean identity involving sine and cosine that I'm thinking of is that sine squared plus cosine squared is equal to 1. Now the really, really interesting thing about this identity, if you haven't seen it before, the insides have to be the same, and no matter what the insides are, this is always true. Even if the insides are both 1/2 theta. Now at first it may seem like cheating a little bit, because we're used to seeing it with only x or only theta, but what if x is equal to 1/2 theta? Then it works, obviously. Okay, good. So now we have this equation from the Pythagorean identity that we know. Also, this is x squared, and this is y squared. So in reality, we actually have eliminated the parameter basically immediately using that identity. And it's x squared plus y squared equals 1. This will allow us to graph things a lot easier. Why? Because x squared plus y squared, if you don't remember from algebra, is just a circle of radius 1, centered at the origin, 0, 0. The only thing though is we have to graph with direction arrows, and we have to be within negative pi and pi, but well, we'll take care of that part soon. But let's just try to sketch this and figure out the arrows at least. So we know the graph is going to look like x squared plus y squared equals 1, which is a circle of radius 1. Okay. Now one thing that we can try to do is we can plug negative pi and pi into x and y individually and see what the largest and smallest x and y can be, and similarly for, so for x and for y individually. But there may be another way of going about that. But for right now, let's at least start with the directional arrows. So I'm going to do that in a different color here. But remember, we're starting at this value. So theta is increasing from negative pi to positive pi. So when you plug in negative pi, what do we get? Well, plugging in theta equals negative pi, just to show right here, we get, let's see, sine of negative pi over 2 for x, and sine of negative pi over 2, well, sine of pi over 2 is 1, sine of negative pi over 2 would be negative 1, because of course sine is an odd function, so the negative comes out. Y would be cosine of negative pi over 2, which is 0. So we get the point negative 1 comma 0, which is over here. X equals negative 1, y equals 0. So we start here, and now what direction do we go in? Well, I guess we can plug in some number in between. I don't want to plug in 0, because when you plug 0 into sine and cosine, you'll get this point, and it's not obvious if we're going in this direction or in that direction. So let's plug something a little closer. If we plug in negative pi over 2, I think is closer to negative pi than 0 is, of course. It's going to be a little harder to see, but when you plug it in for x, you'll get x is equal to, well, negative 1/2 times that is negative sine of negative pi over 4. Sine of pi over 4 is radical 2 over 2. Since sine is an odd function, the negative comes out. Similarly for cosine of negative pi over 4, it's positive radical 2 over 2, because since cosine is even, the negative goes away. So x is going to be a negative value, which will be somewhere over here, and y will be a positive value, which will actually be up here. So it actually seems to be going in this direction, so that's what I'm going to go with. And you can check by plugging in more points, but that certainly is true. And we stop at pi, so when you plug in pi, it's kind of funny, but when you plug in pi, I think you actually go in full circle. But let's see. That may not be right. But we'll have to see by plugging it in. So when we get theta is equal to pi, x will be sine of pi over 2, which is 1. And cosine will be y will be cosine of pi over 2 is what I meant to say. And that's 0. So now we get the point 0, 1, 1, 0, which is here actually. So it does actually stop here. It doesn't go in full circle, which is kind of interesting. And in fact, like I said, if we try to plug these into x and y, we get the following. So we plug pi and negative pi into x, we get sine of pi over 2 and sine of negative pi over 2, which would be 1 and negative 1. So x would be in between negative 1 and 1. Which doesn't tell you anything because in the full circle, the x values are always in between negative 1 and 1. Okay? What about for y? Well, if you plug them into y, we'll get sine of negative pi over 2 is 0. Cosine of negative pi over 2 is 0. Cosine of positive pi over 2 is also 0. So we get that y would be in between 0 and 0, and that doesn't really work out. And I kind of mentioned this in the previous example that we saw involving sketching that curve, the first example we saw anyways. And this doesn't necessarily mean that's true. So just because theta is in between these two values doesn't mean that y is necessarily in between these two values, because all this says is where y ends up and where y starts. Y does start at 0 and y does end at 0. Doesn't mean y can be large as 0, right? Same is true for x, but it's kind of coincidence that it actually does work here. But for y, not necessarily. So plugging in the restrictions on our parameter variable into x and y doesn't quite cut it. Sometimes we actually have to plug in points in between, and we really have no choice. But at least eliminating the parameter gives us a really good idea of what the graph looks like. Otherwise, we would just know these 3 points. We wouldn't know what it would do in between. Okay, and we're going to do one more example. Okay, perfect. So now for this last example here, we're going to eliminate the parameter and then sketch the graph with direction arrows. So how do we eliminate the parameter? We could solve for t by taking ln of both sides, and that works. But what I'm going to realize actually is that y equals e to the negative 2t is the same as e to the t all to the negative 2. Because if you multiply the powers, you get negative 2 for that power. And what do we know about e to the t? It's equal to x from the first equation. Also notice here we don't have restrictions, which will make things a little easier on us. So now we have the equation y is equal to x to the negative 2. And that's basically it, because, well, that's 1 over x squared. And I don't know about you guys, but I remember how 1 over x squared looks. And I guess I'll draw it down here. And it looks something like this. Perfect. The only problem now is, well, what about the arrows? So I'm going to plug 1 and 2, and then negative 1 and negative 2. Well, it wasn't fair for me to say that because these are x values, and I don't want to plug in x values. I want to plug in t values to see the direction. So I want to plug in t going from negative 2 to, so let me do it like this. It would be nice to see what happens when x is negative 2, but then we'd be plugging in weird values. I guess we could plug in weird values. I guess that's not too bad actually. So if we want x to go from negative 1 to negative 2, what would t have to be equal to? So if we solve this for t, it would be ln of x is equal to e to the ln, or ln of e to the t, which is just t. So t is ln of x. So this would be ln of negative 1, which actually can't exist. So again, we're kind of stuck in that situation that I said that you may be stuck in if you're not too careful, where we lose things, we lose information. And the information we're losing here is this side, because now we're basically finding out that x can't be negative, because if x is negative, then, well, you'll have ln of a negative number, which doesn't exist. And that's certainly true. Plugging in any value for t will never result in a negative value for x. So that's unfortunate, actually. Yeah, so I guess we'll just erase this side. Yeah, so how we can be careful to understand that actually would happen from an algebraic perspective, instead of plugging in things and figuring it out as you go along, would have to be somewhere from here to here. So going from here to here, well, we would actually have to arrive at this. So if you were to solve for t in terms of x, there's a realization that x has to be bigger than 0, because that's the domain of ln of x. Okay. Similarly, that restriction would carry over here when you eliminate the parameter. So that's the detail I said you have to be careful of when you translate to a Cartesian equation. I didn't drop that name earlier, but Cartesian equation just means it involves x and y only. But anyways, there it is. So as it turns out, we don't even need these, because x can't be less than or equal to 0. So let's just not even worry about those, I guess. Let's still go from 1 to 2 though. So when is x 1? X is 1 when t is ln of 1, which is 0, and x is 2 when t is ln of 2, which is 0.69, but I'll just say ln of 2. Okay, when you plug a 0 in to y, we'll get also 1, which makes sense because when you plug x into this equation, you get 1 over 1 squared, which is 1, and 1 over 2 squared will be 1/4, which should make sense here too, so we can see that. When you plug in ln of 2, well, e to the ln of 2 is 2, and 2 to the negative 2 is 1 over 2 to the 2, which is 1 over 4. So we're going to go from this value to this value. So from this point, 1, 1, to this point, 2, 1, 4. So we're indeed going in this direction. So in red, let me emphasize that. We're going in this direction throughout. So nice. So we saw a good variety of examples there. And that's really all I wanted to emphasize on for this section. I wanted to thank everyone for watching like usual, and I'll see you in the next videos where we'll uncover more on parametric curves and even different ways beyond parametric curves of graphing things. So it'll be fun. See you in the next videos. Thanks again for watching.